Now, what do we do? Well, the thing we don't want to give up is the ability to work with internal DSLs. Internal DSLs are good because, well, they are very easy to implement. We do want to get over the syntactic limitations, and for that we can use projectional editing, because projectional editing avoids parsing. Avoiding parsing allows us to avoid all the limitations associated with parsing, such as collisions. We also want to get over the semantic limitations, and we can do that by having static analysis. Static analysis allows us to define and implement schema for our DSLs. So it allows us to overcome the limitations there. Now, language workbenches provide us projectional editing and static analysis, and that's where their power is. But Cedalion gives us also the ease of defining internal DSLs. Now, how do we get there? Getting into the middle is not very easy. So the first thing we want to do is consider internal DSLs. For that, we need a host language. So here is a nice list of languages that can maybe serve as hosts. But not just any language. We need an extensible one that allows us to add new language constructs and eventually DSLs. So that rules out some of our favorite, most popular programming languages. Now we want to add projectional editing. Now projectional editing is a little tricky. For projectional editing, we need to define, as part of our DSL definition, we need to be able to define how language constructs are being visualized. You can think about it as some kind of a function, projection function, if you will, that takes DSL code and translates it into some visualization object. Now, since we're doing internal DSLs, both the function that is part of the DSL definition and the code that it has to reason about are both code in the same host language. That means that the host language needs to be able to treat code as data. In other words, it has to be homoiconic. And that rules out any non-homoiconic languages. Now, that's not enough. For a language to be, this projection function needs to run as we're editing code. So for that, the dynamic language will do a much better job than a static one, because a dynamic language only cares about the things that it needs to run. It doesn't care that the rest of the code, well, our application, for example, is only half-baked at the time. So that rules any static languages on our list. But we're not done yet. We need to add static analysis. For that, well, that may come as a contradiction to the fact that our language needs to be dynamic. We can resolve this contradiction by, we cannot use compilation as our means of static analysis, but we can do something else. We can, for example, use or define validators, pieces of code in our DSL definitions that define whether or not a given piece of code in our DSL is valid. Since our language is already homoiconic, we can get the DSL code as input and do that. Well, from the long list of languages we started with, we are down to about 2. And trust me, there are not much more than that on the, generally. And now we have to make a choice. So for Prolog, we chose, for Cedalion, we chose Prolog or logic programming as our base semantics. So, what is Cedalion? Well, It's an LOP language, which means it's a language designed for LOP. It's extensible, homoiconic, and dynamic. It's statically typed as a means of static analysis, but its type system is defined from within the language and not an integral part of the language. It uses projectional editing instead of editing the code as text. It's based on logic programming, but this choice is merely provides its base. On top of logic programming, we can define other domains and other paradigms, like we did with BNF. And it comes with a language workbench, so we can edit code. So the Cedalion workbench is an Eclipse plugin, and it works by querying the Cedalion program in order to know what to do and how to represent and allow users to edit things.